2.8 trillion. Beat.
Mhm.
That is a massive, almost incomprehensible number.
Yeah, it really pushes the limits of what we can easily conceptualize.
It's hard to even picture that scale physically. We hear these massive numbers thrown around in AI constantly now.
Right, like it's just a high score in a video game.
2.8 trillion parameters, 1 million tokens of context window. It sounds like we're just building heavier machines.
People assume it's just, throwing more GPUs at the problem.
Right. It sounds like pure brute force. But brute force size isn't the real story here.
Not at all. I mean, brute force actually stops working at this scale.
Welcome to the deep dive. We're looking at Moonshot AI today. Specifically, we're unpacking their new Kimi K3 architecture.
It's a fascinating paper.
We have a very clear mission for this conversation. We're going to look at 3 specific design choices: Stable LatentMoE, Kimi Delta Attention, and Attention Residuals.
And these 3 choices prove something incredibly important about the industry. The future of AI isn't just about getting bigger.
It's about getting dramatically smarter with the compute we already have.
Exactly. We have to be more elegant.
Let's start with the first massive bottleneck. To understand how a model this large doesn't just immediately crash a server, we have to look at physics.
Yeah.
We have to look at how data physically moves.
Because a 2.8 trillion parameter model is unbelievably heavy. Does it magically sit inside one computer's memory?
You'd need a warehouse of machines just to hold it.
Exactly. So Kimi K3 uses a very specific architectural design. It uses a mixture of experts architecture.
Let's define that clearly. A mixture of experts routes data only to specialized subnetworks.
Yeah, that's exactly right. You can think of it like a massive corporation.
With different departments.
Right. Kimi K3 has 896 of these specialized experts built in, but it doesn't use all of them at once.
It only activates 16 at a time for any given token.
Which saves massive amounts of computational power. You're only running a fraction of the total model at any given millisecond.
But here is where the physical bottleneck actually happens. Beat. These 896 experts don't all live in one place.
No, they're spread out across hundreds of different physical GPUs.
They are literally housed on different microchips.
Connected by physical cables.
So when a token needs to be processed by an expert, its data has to travel.
Right.
It moves physically between these computing chips.
And that's the core problem. It's not just a math problem anymore, it's a physics problem.
Moving heavy data across GPUs takes real physical time.
It takes time and it eats up massive amounts of electrical power.
If you're building a massive AI system, your biggest enemy is often just traffic.
Yeah, and the communication costs become incredibly high. Sometimes moving the data costs more time than actually calculating the answer.
Which completely ruins the cost savings of using a mixture of experts in the first place.
It totally defeats the purpose.
So how does Moonshot AI actually fix this traffic jam?
Their solution is something called Stable LatentMoE. It fundamentally changes how the data is transported across the hardware.
It runs the expert computations inside a smaller latent space.
Which means it mathematically compresses the data representation before sending it.
Let's define that term for a moment. A latent space is a distilled, compressed mathematical summary of data.
Perfect definition. And by working in this compressed space, they get 2 massive benefits.
First, the individual experts have far less raw data to chew through.
Right. And second, far less physical information needs to move across the cables between the GPUs.
Think of it like a massive folder of high-resolution files. You wouldn't just attach that massive folder to an email raw.
You'd instantly crash your email client if you tried.
Exactly. You'd zip that massive folder into a compressed file first, then you email it across the Office network.
It's the exact same principle here. You compress the heavy data into a latent space, send it, process it, and then unpack it.
But reducing the data size is only one part of the routing problem. The router also needs to spread the tokens evenly across the hardware.
Yeah, because you have 896 experts waiting for work. You can't just send all the tokens to the same 5 experts.
That would just create a localized traffic jam on those specific chips.
So Kimi K3 implements a clever technique called Quantile Balancing.
Zhenlin Su actually broke this concept down beautifully on X recently. Standard routers usually score tokens and send them based on a rigid absolute threshold.
Which requires incredibly sensitive heuristic tweaking. It's a nightmare.
If the absolute scores drift during training, the balancing breaks completely.
But Quantile Balancing avoids that rigid trap. It compares router scores by their relative position instead.
It's basically grading on a curve instead of requiring a perfect test score.
Right. This completely removes those fragile balancing settings.
It eliminates the need for constant manual heuristic updates.
And it achieves flawless sequence-level load balancing. Plus, it does it without adding any artificial loss penalties to the training process.
Okay, let's unpack this with a probing question. Does compressing all this data into a smaller latent space cause the model to lose important nuances?
Not significantly, if it's trained correctly. The network trains itself to preserve the most critical semantic features during that compression phase. It learns what matters and what doesn't.
So it essentially learns to keep the skeleton and drop the fat.
Exactly. 2-sec silence. Which perfectly sets up the next massive architectural challenge.
We've solved the width of the model. We're routing data efficiently across hundreds of physical GPUs. Now we have to solve the length.
We have to talk about how the model remembers what you're saying.
How do you manage a massive 1 million token memory context?
Doing that without completely running out of RAM is a monumental engineering hurdle.
Let's put 1 million tokens into a real-world perspective. That isn't just a long prompt.
No, it's an enormous ocean of text.
It's like loading 10 thick novels directly into the computer's active memory.
Or dumping an entire corporate software codebase into a single chat window.
And you're asking the model to simultaneously remember and instantly reference every single line.
Standard attention models use a mechanism called a KV cache to handle this.
Let's quickly define that term as well. A KV cache is a massive memory system storing past token data.
But standard attention becomes exponentially more expensive as that context grows.
Think of a standard KV cache like a massive rolling scroll of parchment. Every time you add a new word, the scroll gets longer.
And heavier to read? By the time you reach 1 million words, unrolling that scroll takes massive compute.
The memory requirement rises incredibly fast.
It does.
The KV cache just keeps getting larger and larger during the decoding phase.
It simply does not scale to 1 million tokens cleanly. The servers would literally run out of physical memory just holding the cache.
So, Moonshot AI completely reimagined this with Kimi Delta Attention. They call it KDA.
KDA takes a fundamentally different mathematical approach to memory.
It replaces that endless scroll with a matrix-based recurrent memory state.
Instead of a constantly growing KV cache, it maintains a fixed size state.
Think of it less like a growing scroll and more like a fixed-size whiteboard.
That's a great analogy. When a new token arrives, KDA doesn't just tape a new piece of paper to the end.
It updates the existing whiteboard state.
Right. It updates the mathematical relationships between the keys and values. Then it uses that updated state to create the immediate output.
The beauty is that the memory footprint doesn't infinitely grow with the sequence.
The whiteboard stays the exact same size, even at 1 million tokens.
KDA makes this work through two highly specific mechanisms. The first is called fine-grained gating.
This acts like a bouncer for the model's memory. It controls what specific vital information should stay on the whiteboard.
And more importantly, it controls what irrelevant information slowly fades away to make room.
The second major improvement they added is chunk-wise processing.
Standard attention calculates the sequence token by token, one after another.
But chunk-wise processing splits the sequence into smaller, manageable blocks.
Right, and that allows the GPUs to calculate those chunks in parallel.
Exactly. It handles multiple blocks of text simultaneously before updating the recurrent state.
Kimi Linear is the specific model variant that combines this KDA with global attention.
And it beautifully balances raw processing speed with accurate pinpoint retrieval.
The reported performance stats on this combination are genuinely staggering.
There really are. They reported using up to 75% less KV cache memory.
And they achieved 6 times faster decoding speeds at the 1 million token mark.
6 times faster.
Whoa. Beat. Imagine scaling to 1 million tokens and actually getting faster.
It's wild.
It completely defies our standard intuition about how software should behave under a heavy load.
It's a brilliant piece of engineering. They turned a linear scaling problem into a constant size operation.
But this raises a really fascinating probing question. How does the fine-grained gating actually know which parts of a massive document to let fade away?
It learns complex relevance weights during the training phase. It prioritizes keeping structural markers and conceptual anchors while safely dropping redundant linguistic filler that doesn't really change the overall meaning.
It develops a highly selective, incredibly efficient working memory.
Precisely. It learns to focus.
2-sec silence.
No.
So we've successfully handled the data traffic. We've conquered the context length.
But there is one final dimension we must tackle.
The depth.
The depth.
How does a specific thought survive traveling through hundreds of neural layers?
Think about human reading comprehension for a second.
It's a really helpful parallel here.
When we read a long, incredibly dense academic paper, we often forget the beginning.
We entirely lose our train of thought halfway through the document.
Deep AI models face a very similar mathematical degradation.
As information moves down through hundreds of deep layers, the core signal degrades.
Standard neural networks use residual connections to fight this.
They try to add every previous layer's output forward, using the exact same fixed weight.
But in incredibly deep models, that rigid approach backfires. The hidden state simply blows up with too much noisy data.
Individual layers entirely lose their specific sharp influence on the final output.
The original signal simply washes out in a sea of mathematical noise.
I still wrestle with prompt drift myself. Beat. It's incredibly frustrating when a model just forgets my core instructions by the end of a deep task.
Yeah, that prompt drift is exactly the degradation we are talking about. The model's deep layers literally lose sight of the initial instruction.
This is exactly where Kimi K3's attention residuals come in.
They completely scrap that old fixed path routing method.
Instead of a rigid path, each layer uses dynamic attention.
It actively selects useful representations from the earlier layers.
It bases this selection entirely on the current input it is processing.
The connection weights constantly shift, depending on what the model specifically needs right now.
So if layer 90 suddenly needs a specific verb from layer 2, it just reaches back and grabs it.
Exactly. It isn't forced to accept a watered-down average summary of layers 3 through 89.
This dynamic routing improves deep models in two vital ways.
First, the core information stays incredibly crisp across hundreds of layers.
Second, the output values and the training gradients remain beautifully balanced.
You don't get those massive mathematical blowups that usually crash deep training runs.
So this effectively gives the model a sort of active hindsight while it's processing.
Yes. It can continuously look backward at its own previous computational layers to fetch exactly the context it needs in that precise millisecond.
It dynamically reviews its own past thoughts to stay perfectly on track.
It's a fully dynamic, self-correcting cognitive process.
This is a perfect moment to let these concepts settle. Let's take a brief pause here, mid-roll sponsor break. All right, let's bring all of these distinct architectural threads together.
Each individual part of Kimi K3 solves a very different physical constraint.
Kimi K3 isn't just a giant brute force statistical model.
No, it is an absolute masterclass in treating AI architecture as a complete holistic system.
Every component is carefully designed to work together to bypass physical hardware limits.
Stable LatentMoE specifically handles the data traffic.
It completely reduces the heavy physical networking work inside the expert system.
Kimi Delta Attention specifically handles the active memory.
It drastically lowers the computational cost of processing incredibly long context windows.
And finally, Attention Residuals handles the deep layer cognitive focus.
It keeps the useful, specific information perfectly clear across hundreds of layers.
The ultimate takeaway from unpacking this architecture is very clear.
Better AI design vastly improves speed, memory efficiency, and training stability.
And it achieves this without endlessly relying on brute force parameter counts.
It's entirely about doing far more with the physical compute we already possess.
It represents a fundamentally smarter, more elegant way to build intelligence.
Which leaves me with a lingering, slightly provocative thought for you.
Beat.
We've just seen how a massive 2.8 trillion parameter model can be engineered to run this efficiently in a data center. But what happens when these exact architectural tricks are applied locally?
Oh, wow.
When the compressed latent spaces, the fixed-size KDA memory, and the dynamic residuals are applied to small models.
Like models running locally entirely offline.
Right on the silicon of the phone in your pocket.
That optimization completely changes the entire future landscape of local compute.
It really does, Pete. Thank you for joining us on this deep dive. We always appreciate you taking the time to explore the bleeding edge of these systems with us. Until next time.